Okay, so we are looking at enolate chemistry, um, and this will begin from, again, the discussion of what is an enolate. And we pointed out that I can take a carbonyl compound at the aldehyde level, and the alpha carbon is the carbon attached to the carbon of the carbonyl, right? And the H attached to the alpha carbon would be called the alpha H. Enolates, of course, are the compounds formed when the carbonyl compound is deprotonated. So these are relatively acidic and generate the corresponding enolate. The enolate, of course, as we've mentioned before, is an ambident ion, meaning that the the nucleophilicity can be felt at both the carbonyl oxygen and at the alpha carbon. So there's a delta minus here and delta minus minus minus. Much of the negative charge, understandably, will be supported by the O, which is more electronegative. I will remind you that carbonyl compounds themselves can tautomerize, but the position of tautomerization actually favors, under normal circumstances, the keto version. So this is the keto species, this is the enol. And if I were to deprotonate the enol, the species that I would generate would be the anion of the enol, and that is called the enolate. Right? So the enolate ion would be that species. And again, the term we use for it is ambident, meaning that it has two teeth. It's an ambident nucleophile. I mentioned in class that the bulk of the reactions we will see from enolates is at the alpha carbon, even though more of the negative charge is actually supported by the O. There's a larger concentration of negative charge in the O. The point, though, is that O is a relatively electronegative atom, and so it's relatively comfortable with the electron density. But the carbon is not, and therefore the carbon is more desperate to get rid of the electron density. So much of the nucleophilicity of the enolate is actually felt via the carbon. Okay, so enolates undergo a variety of reactions because they are nucleophilic, and as I mentioned, the bulk of the reactions of enolates actually occur at the carbon. Because that's a species that's more desperate to get rid of electron density. And among the reactions that they undergo are the following. And I'm just going to see if I can do 5 of these and see if I can capture all. So they react with haloalkanes to give the substituted compounds. This is actually very useful because, as I've mentioned on a number of occasions, one of the axes, if you will, of organic synthesis is carbon-carbon bond formation and carbon-carbon bond breakage, right? So in general, when you do organic syntheses, they kind of hang on 3 axes, right? There's functional group interconversion, there is redox, and then there's carbon-carbon bond formation and breakage. And so this is a reaction where we actually are making a carbon-carbon bond. We're going to highlight these reactions in a bit. Enolates also react with oxyranes, followed by water, and that process generates the corresponding alcohol. And again, wait a minute, I'm missing one carbon. All right, generates the corresponding alcohol. And these 2 carbons of what was once the oxyrane are these 2 carbons. They react with other aldehydes and ketones in a reaction called the aldol reaction, which we will spend some time on. And the aldol reaction, the products of the reaction are a beta hydroxy carbonyl compound right, which is called an aldol. This is a beta hydroxy carbonyl compound, and that's called an aldol. We will see as well, when we look at this stuff, that aldols themselves are labile, and on warming, aldols dehydrate. This is the third class of unstable alcohols. Aldols will dehydrate to generate the alpha-beta unsaturated carbonyl compounds. And as we'll see, the ease of dehydration depends upon the substitution pattern of the aldol. I'm just going to make a little point here. So we've seen now several classes of alcohols that are unstable, right? We've seen gem diols, which are unstable, and they spontaneously dehydrate to make the carbonyl compound, right? So these lose water to make the carbonyls. We've seen enols, which tautomerize to give rise to the corresponding carbonyl compound, right? And now we're seeing aldols, which, depending upon the substitution pattern, will dehydrate. Oh, there should be an H here. Will dehydrate to give rise to the corresponding alpha-beta unsaturated carbonyl compound, right? So there are three classes of unstable alcohols that we've met, and you want to be aware of those, because you want to look out for those, because their chemistries are really quite interesting. Carbonyl enolates will also react with halogens, and they will give a series of products. And essentially what happens is we'll end up with the monohalo compound, the dihalo compound. I'm going to erase this bit so I'll have some room. Okay, so hopefully you've had this in your notes. So you get the monohalo compound, the dihalo compound. If there is enough of the reagents of the halogen, you get the trihalo compound. And then eventually this gives rise to a carboxylate and CHI, well, CHX3. CHX3 is called a haloform, and we will talk about this in some detail in a little bit. And then there's a series of reactions of enolates which are called Michael type reactions. Michael type reactions, and we will look at those in some detail. Okay, so let's begin by looking at the first reaction, which is the reaction of enolates with haloalkanes. And the scenario that we want to paint is the question of converting an unsymmetrical carbonyl compound, for example, a methyl cyclohexanone, into, let's say, its methyl derivative. So you can imagine then that I can either convert this compound into this methyl derivative, which is the symmetrical product, or I can convert it into the isomer, which is the unsymmetrical product. And in fact, I can actually generate each of those compounds pretty much at will. So the way the reaction goes is the following. If I treat the carbonyl compound with a base, with any base, there are two different H's that I can remove. There's HA, and of course there's HB. If I remove HA, right, so if I remove HA plus, what that gives me is the enolate, which has this structure. So I'll have a minus charge here, double bond O, and this enolate is resonance stabilized and is present. I can show this resonance form. But as I mentioned, the major resonance form of an enolate is actually this one, where the negative charge is on the more electronegative O. And so much of the enolate then has really what I might call alkene character. If I ignore the O minus, this really is sort of an alkene. And this alkene has 1, 2 alkyl groups on it. So it's a di-substituted alkene. On the other hand, if I remove HB plus, I will make this enolate. Right? I'll make this enolate. And that is resonance stabilized as well. And the corresponding resonance form is going to look like this. And this species has 1, 2, 3 R groups on it. So this is a tri-substituted alkene unit. So of the 2 enolates, this one is actually more stable. This is the more stable species. We've seen this story play out before, right? If I have this haloalkane and I want to do chemistry by removing HA, I would use the bulky base, because the bulky base would shy away from the more crowded site. This would be my major product. If I use T-butoxide as the base. On the other hand, if I want to make this alkene, I would use a small base, because a small base is not afraid of the bulky site, and so it picks the site that gives rise to the more stable product. Remember, this is classic Hammond-Leffler postulate, right? The reaction is an endotherm, and so the transition state is going to be product-like. So the pathway that gives rise to the more stable product vis-a-vis this alkene is going to occur faster, right? And it's going to by the lower energy transition state. So we'll get more of the tri-substituted alkene than we would of the mono-substituted alkene, unless we use a bulky base, which makes the reaction at that site politically difficult. So the same idea applies to these. If I want to get chemistry that removes HA instead of HB, I will use a bulky base, which will shy away from this site and take the next best prize, which is this proton. If I use a small base, well, then that has no difficulty going either A or B, so it would prefer to do B, because loss of B plus or HB plus gives rise to more stable alkene. So I'm going to use that logic in designing my synthesis. So here's what I will do. If I treat my ketone with a bulky base, and for carbonyl chemistry, the bulky base that we use is LDA. And LDA is an acronym for lithium diisopropylamide, which is this species. It's the lithium salt, right? And it's got 2 isopropyl groups. So it's lithium diisopropylamide, right? Oh, crikey. Lithium diisopropylamide is the quintessential example of a strong sterically hindered base. In many ways, it is analogous to T-butoxide, right? So if people are thinking of a strong sterically hindered base, they're thinking of either the LDA or the T-butoxide, right? Both of those would fit the bill. If I treat this carbonyl compound then with LDA, what's going to happen? Well, I'm going to get both enolates. Again, I'm going to get both enolates. I'm going to get this enolate, plus I'm going to get this enolate. Okay? But I'm going to get this one as my major product. Well, that's great, because in fact, if remember now, what I want to do, I'm trying to do the first synthesis. I'm trying to convert as this species, right? The first one I'm doing is trying to make this compound, right? This is what I'm trying to make first. So this enolate will be my major product. Now, life would have been great if I could separate these 2 enolates and use, so I could resolve the mixture and then just simply isolate this compound and use it. Turns out that the enolates are exceedingly difficult to separate. But if I treat the enolate with trimethylsilyl chloride, and you've seen this reagent before, we used it before, when we're trying to do protection of alcohols. And how did that work? The alcohol would act as a nucleophile and attack trimethylsilyl chloride. right? And we get an SN2 reaction, which kicked out the chloride, and we ended up with ROH, the silyl group, right, Ne3, and there's a plus charge here, and then the pyridine was a solvent, came along, sucked the proton off, and I made my product, ROTMS. Well, we're going to do exactly the same thing, because you want to remember that this is only one resonance form of the enolate. The other one, which actually is the major resonance form, would be these things. And obviously, if the alcohol, which has no negative charge on the O, is a nucleophile, well then surely this species is an even stronger nucleophile. So if I treat the mixture of the enolates with TMSCl, that will generate two silyl ethers. These ethers would be this one, TMS, right? And this one. Oh, shoot, wrong place. Let's just wait. All right, I'll get two ethers. All right, OTMS. So this enolate would give rise to that. These are called silyl vinyl ethers, right? These were simply called alkyl silyl ethers because the R group was simply alkyl, it was sp3 hybridized. These R groups are vinylic, right? This is a vinylic group, so they're called silyl vinyl ethers, and of course they're alphabetized. So alkyl silyl, silyl vinyl. It turns out, just by sheer blind luck, that the silyl vinyl ethers chromatograph beautifully. So I can actually take my mixture, I'm going to replace this now, I'm going to take my mixture of the silyl vinyl ethers and do a separation. The separation is typically done by chromatography, but I'm just going to say separate. And I will end up in one container with this species, OTMS, which, by the way, I'm going to redraw this as SiMe3. Okay, so I'll end up with this. Now understand, this enolate with a large base, this enolate was my major product. So it stands to reason if I feed the mixture, which contains more of this one, TMSCl, I will end up with more of this species. So large amounts of this one will give me large amounts of this. So this is my major ether. So when I separate, I'm going to dump the minor one and keep the major one. Fantastic. Well, we're close. I don't want the silyl vinyl ether, though. I want the enolate. So how do I regenerate the enolate? And the answer is I'm going to treat it with tetrabutyl ammonium fluoride. And it's actually kind of amazing. Tetrabutyl ammonium fluoride in many ways acts like ammonium fluoride. It contains an ammonium ion and a fluoride ion. The reason we are getting chemistry, and I'm going to point this out, the reason we are getting chemistry at the O, because remember I said, most of the chemistry of enolates happens at the carbon. This reaction actually happens at the O, and the reason is the oxygen-silicon bond is exceedingly strong. That's why the world is full of sand, because the silicon-oxygen bond is very strong. So the reaction is actually driven by thermodynamics. But even stronger than the oxygen-silicon bond is the fluorine-silicon bond. So fluoride of tetrabutyl ammonium fluoride attacks the silyl vinyl ether and regenerates the enolate. And this should be very familiar to you guys. This is essentially a masking, unmasking, right? Or protection, deprotection deal. Although it's not so much a protection because we weren't going to hurt it, right? But we were masking the enolate, which we couldn't separate, as something we could separate. And then we separate and carry out our unmasking. And of course, the other product of this reaction would be trimethylsilyl fluoride. Trimethylsilyl fluoride. Okay. Now, this is the only species I have. If I treat that with methyl chloride, then I'll get a nice simple SN2 reaction. bang, bang, and I make my product. So I now get a sample of the pure material if I used LDA, TMSCL, resolve the mixture to isolate the appropriate silyl vinyl ether, release the enolate using tetrabutyl ammonium fluoride, and then use the enolate to carry out my alkylation reaction. Great. What if I wanted the other isomer? How would I do that one? Well, I would do almost exactly the same thing. It's just that the character of the base would change. So here I am. I'm going to treat this now with hydroxide, which is a small base. Hydroxide, being a small base, is going to give rise to the product that actually is the more stable one in larger amounts. So I'll make this enolate as my major species. This one will be minor. Oh, crikey. This one will be minor. Stop it. I can't resolve these, so I'm going to treat them with TMSCl, and that's going to give me the very same two silyl vinyl ethers. This one plus this one. And again, because this enolate is major, I would expect that this silyl vinyl ether would be major. I'm going to separate them by chromatography again. That would give me the desired material, which is this one. I will treat it with tetrabutyl ammonium fluoride. So this is exactly what we're doing before. And the fluoride ion comes in, attacks, and I regenerate my enolate, which I'm going to draw slightly differently this time. And if I feed that methyl chloride, I'll carry out a simple SN2 reaction, and that will generate my target product, which is the gem dimethyl species. This sequence and this one above it are virtually identical, right? They're virtually identical. The only difference is which silyl vinyl ether we capture as the major product, and as a result, which pure enolate we generate from the unmasking. So I will carry out selective alkylation of my carbonyl compound by choosing hydroxide or LDA as the base. That's the only way they differ. And then the following steps are exactly the same. So it's some base, whichever one is appropriate, followed by TMSCl, then chromatography or separation, followed by tetrabutyl ammonium fluoride, then whatever alkyl group that you desire. Okay, so that's alkylation of enolates. The other reactions, let's see, that we looked at, is reaction with oxiranes. And the reaction with oxiranes is, so let's call this reaction number 2, with oxiranes. This is actually fairly simple. We've seen oxirane chemistry before. So I can take my carbonyl compound, treat it with hydroxide. That will generate the enolate. If I treat the enolate with an oxirane, right, then I'm going to have a nice simple SN2 reaction. That will generate this species, which will pick up a proton from water as a second step, and I make my target alcohol, or my target product. All right, so let's see, 1, 2, yeah. So I make my target product. Okay, and of course, this is an equilibrium, and I'll lose hydroxide in this step. But that's O minus giving O minus, so we're okay. The third reaction is a bit more involved, and this is the aldol reaction. So if you think it through, if I treat a carbonyl compound with, and let's start off with ethanol. If I treat ethanol with hydroxide, this is not surprising, I'm going to generate, and I'm going to turn this around a little bit, I'm going to generate the corresponding enolate. But I have made the enolate in a system containing the aldehyde, right? Because not all of the aldehyde would have been converted. Well, aldehydes are great electrophiles. Enolates are pretty darn good nucleophiles. So it's not surprising that the nucleophilic daughter species will go after the electrophilic parent. And what I will get, this is an equilibrium, would be this species. Right? Now let's count our carbons to make sure we know where we are. Let's give these numbers. Carbons 1 and 2 of my parent. So let's make them 1 and 2 here. And let's call this one A and B. Well, 1 and 2 are here. A and B are here. So if you look at this alkoxide, this is an aldo alkoxide or alkoxy aldehyde. The carbonyl of the enolate remains intact. The carbonyl of the aldehyde, the neutral aldehyde, suffers, right? It suffers a reduction because the pi bond breaks. What was on a double bond O, what was once a double bond O, now becomes a single bond O with a minus charge. The H is still there, I just haven't shown it in the bond line. The methyl B is still there. The bond that I made is this bond. It's the C2Ca bond. Now, eventually what will happen is this will pick up a proton from water, right? We're going to lose hydroxide, and I'll end up with this species. And this species, here's my carbonyl carbon, this is my alpha carbon, that's my beta carbon. This is a beta hydroxy aldehyde. And because it has both aldehydic properties and alcoholic properties, because it's an OH, then it's called an aldol. So aldol really is a portmanteau word. It's a composite word that contains both aldehyde and alcohol. Now, aldols are thermally labile. They're thermolabile. And if you heat the aldol, it will dehydrate. Now, obviously, there are two ways I can dehydrate. I can lose an H from the alpha carbon, and that will generate the alpha-beta unsaturated carbonyl compound. I'll get that compound. Or I can lose an H from the gamma carbon, and what that will give me will be this compound. And it's a no-brainer. This one is conjugated, right? Double, single, double. This one is not conjugated. And so I don't see the unconjugated product at all. I always see the more stable product. So we end up then with this species, which is the alpha-beta, right? So alpha-beta, it's the alpha-beta unsaturated aldehyde as my product. Well, even though this reaction happens with aldehydes, there's no reason why it couldn't happen with other species. So for example, if I treat acetone, right, with base, then the same menu of reactions will happen, right? The base will come in, pull off the H+, I would make my enolate. The enolate is generated in a matrix containing the parent, which is an electrophile, and therefore the enolate will scavenge its parent, okay, and generate, the beta hydroxy carbonyl compound. And this is important, right? My product will always be beta hydroxy, so carbonyl carbon, alpha, beta. And in fact, I can just draw this as my unit and then try to populate it. So for example, if I go back, I'll say, let's call this carbon 1, 2, 3, and let's call this carbon A, B, C. Well, this is 1, that's 2, that's 3. 3 is a nucleophile that initiates chemistry. The carbonyl of the nucleophile remains intact, right? So 1, 2, 3, 1, 2, 3. Carbon 3 attacks carbon B, which was once doubly bound to O. It's now only singly bound to O. So this is B. But attached to B with two methyl groups, A and C. So attached to B are two methyl groups, A and C. So that would be my alkoxide. If I treat this with moisture, the alkoxide reacts with water, pulls off the proton, I lose hydroxide, and I make my corresponding, oh man, why is this sliding over? I make my corresponding beta hydroxy compound. Right? In the bad old days, because this compound was formed from a ketone, it used to be called a ketol. So aldehydes gave aldols, ketones gave ketols. Nobody makes that distinction anymore. And so I'm simply going to call this one an aldol as well. You would notice again, aldols are beta hydroxy carbonyl compounds, right? Carbonyl carbon, alpha beta. So that is the common motif. That is always the species we generate. As we did before, if I heat this one, it's going to dehydrate, pulling off one of these H's to give rise to the alpha-beta unsaturated carbonyl product. If you notice though, this one has one, two, alkyl groups attached to it, because I wouldn't consider this an alkyl group. I've got 1, 2 alkyl groups, whereas this one had only one alkyl group. So what the consequence of that is that this alpha beta unsaturated carbonyl compound is not going to be as stable as this one, which has 2 R groups feeding the alkene. As a result, because this is more stable, this compound forms faster, right? Because we're doing a dehydration, right? So we're making an alkene. Those reactions are endothermic. I'm going to make this compound faster. In other words, I don't need to heat it quite as hot or for quite as long. So maybe, and I'm just tossing numbers out here, I might need to heat this one maybe at 80 degrees Celsius to make a good yield of this compound. But maybe to do this one, I might just need 60 degrees Celsius, right, for the same length of time to make that compound. So the more stable my alpha beta unsaturated carbonyl compound is, the more facile is its formation, right? And this is simple Hammond-Leffler stuff, right? The more stable my product in an endotherm, the more facile the reaction. The more stable my product, the more facile the reaction. Classic Hammond-Leffler. Well, we have a little problem, and the problem is that, actually, I think I have space on this page. Well, not much. Well, a little bit, but whatever. Well, I'll take it. The problem is that if we were, for example, to treat, you know what, I'm going to be a little bit greedier. If we were, for example, to treat a mixture of carbonyl compounds. So in other words, let's look at what's called a mixed or crossed aldol reaction. In other words, what would happen if I used ethanol and propanone, which people will still call acetaldehyde and acetone? What would I get if I treated that mixture with hydroxide? What would be the structure of the enolate? Well, I'm sorry, what would be the structure of the aldol? Well, let's see. If I treat this mixture with hydroxide, both of these carbonyl compounds have an alpha H. Both of those alpha H's are relatively acidic, and I could not force the hydroxide to attack one of them or the other. So both will happen. So let's see what will happen when the enolate from ethanol is generated. That enolate will look around and see two different electrophiles. It'll see its parent and it will see the acetone. So it will scavenge them both. When that enolate attacks its parent, it's going to give rise to a beta-hydroxy carbonyl compound, which is that compound. And we're all adults. I'm just going to go ahead and put the H on it, right? Because the alkoxide will pick up a proton and make the OH. So I have H, carbon-carbon, H, carbon-carbon. This carbon is the one that used to be the carbonyl of the aldehyde. There is an H understood here, and this methyl is here. So that's one product. But of course, that enolate can attack acetone, and if it does, it'll make the alpha, beta, and unsaturated carbonyl compound, which is this one. Good God. It'll make the aldol, which is the beta hydroxy carbonyl compound. These carbons, 1, 2, are these carbons, 1, 2. This carbon is this carbon. And attached to it with 2 methyls, those methyls are still there. Okay? That looks kind of weird. Oh, for heaven's sake. Right, so what I'll get would be this compound, double bond O, OH, and then there'll be 2 methyls. And I'm leaving out the stereochemistry. So that's 2 products. But the other enolizable compound is the acetone. And when the acetone makes an enolate, it will turn around and attack both its parent, right? It can attack its parent, as well as the intact aldehyde. When it attacks its parent, it's going to give rise to this compound. Right? I'm going to make that compound. When it attacks the aldehyde, it's going to give rise to this compound. Right? And again, I am going to start off drawing the beta-hydroxy carbonyl compound and then just flesh it out. So these 1, 2, 3 carbons are here. 1, 2, 3. This carbon, right, because this is attacking here, this carbon used to be the carbon of the ketone, attached to which are 2 methyls. They're still here. 1, 2, 3, 1, 2, 3. This carbon was the carbon of the aldehyde, attached to which there's a methyl and an H, methyl and an H not shown. Now, what's interesting is that when the enolate of the aldehyde, attacks acetone, I get this compound. When the enolate of acetone attacks the aldehyde, I get that compound. Now, these compounds are isomers, right? C1, 2, 3, 4, 5. C1, 2, 3, 4, 5. 1 HDI, 2 O's, 2 O's. So these are isomers. So when I do this reaction, I actually get 4 products in very comparable yields. Comparable yields because both of these protons are equally acidic, and both the aldehyde and the ketone are pretty good nucleophiles. Now, in all fairness, the aldehyde will be attacked faster than the ketone. So I'll get more of this than that, and more of this one than that one. So the yields won't be 25%, right? I'll probably get maybe 30-30 and then 20-20. Okay, but I'll get significant yields of all 4, which is a nightmare. Because now I'm going to have to separate, let's say, I don't know, let's say maybe I wanted to make this compound. I'm going to have to separate this compound, which is already in bad yield, from 3 other compounds of very similar molecular masses, very similar physical properties. So it's a nightmare to attempt to separate those. So what we might want to do then is decide, well, is there a way that we can do an aldol reaction, a crossed aldol reaction, that is reasonable, that is practical? And the answer is absolutely. So how do we do a practical crossed aldol reaction? How do we do a practical crossed aldol reaction? And the answer is by recognizing what the problems were. The problem with this aldol reaction, this one, is that both of these compounds were enolizable. I'm going to write that word down. Enolizable means that they're capable of forming enolates, that there is an acidic proton, right? There is an H that is alpha to the carbonyl that can be pulled off, right? There's an H here, there's an H here. So these compounds can form the enolates. Therefore, they are enolizable. And because I made two enolizable species, they would turn around and attack both parents. And therein lies a problem. So I could actually do a crossed aldol reaction that's practical if I only have one of the two carbonyl compounds that's enolizable. Well, are there carbonyl compounds that are non-enolizable? The answer is there are a bunch of them. For example, methanol does not have an alpha H. It has a carbonyl H, but not an alpha H. Benzophenone is an example of a compound that is non-enolizable. Right? It's got a carbonyl, but there are no H's here or here. Let's see. So chloral is an example of a compound that's non-enolizable. Benzaldehyde is an example of a compound that is non-enolizable. And there are lots of other examples, right? So there are many examples of carbonyl compounds that are non-enolizable. So if I want to do a practical cross-aldol, here is the way I will engineer it. So I will have a dropping funnel, which I'm not even going to attempt to draw a dropping funnel, that I will be dropping into a reaction flask. This is meant to be some sort of an Erlenmeyer flask, although to look at it, you couldn't even imagine that. And I'm going to have this stuff on a stirrer of some sort. So this is not an eye, that's a stir plate. I'm going to have a stir bar in the matrix. This is the tap. So let's say the reaction was between something enolizable, let's say maybe acetone, and then something non-enolizable, let's say benzaldehyde. And my intent is to make the enolate from acetone and have it attack the benzaldehyde. So what would I get? I'm going to get a beta-hydroxycarbonyl compound. 1, 2, 3, 1, 2, 3. The bond I'm making is this one. This carbon used to be the carbonyl carbon. Attached to it is a phenyl group and an H. The H is not shown. So this is the product I want to make. So here's what I'm going to do. I am going to put the non-enolizable carbonyl compound, the benzaldehyde, in the reaction flask together with hydroxide. Because I know the compound does not have an acidic H, so hydroxide is not going to mess with it. In the dropping funnel, I'm going to put my enolizable carbonyl. And I will add, drop by painful drop, the solution of my acetone, or it could just be the acetone. This solution is going to be stirred rapidly, right? Rapid stirring. So here's the logic. When I open the tap and the first drop of acetone hits, the acetone is going to react with hydroxide and give rise to the corresponding enolate. But that's an equilibrium, right? I mean the enolate and water. That's an equilibrium though. But remember now, all the hydroxide is already in the flask, right? So now I'll be 0.5 molar hydroxide, lots of moles of hydroxide in the flask. And I have only added a single drop of the acetone. So there is a massive excess of hydroxide as far as the single drop of acetone is concerned. And because I am stirring the solution rapidly, as soon as that drop hits the solution, it is engulfed by trillions of hydroxide molecules, of hydroxide ions. So by Le Chatelier's principle, it takes the equilibrium and pushes it essentially to completion. So that since proton transfer is very, very fast, essentially as soon as the acetone hits this solution and it's gobbled up by protons, all of it instantaneously in the space of 10 to the minus 13 seconds is converted to the enolate. So when the enolate looks around for an electrophile, it sees none of the parent. because all of the parent has been converted into the enolate. So it can't go after the parent. The only electrophile it will find in the system is the benzaldehyde, right? The one that I had in the mixture with the hydroxide. So it's the only pony in the game. So the enolate attacks the aldehyde. We end up with the beta hydroxy entity, which I always draw, and then that picks up a proton from water and eventually makes my target. Okay, then the second drop of the ketone hits. It'll be gobbled up by trillions of hydroxide ions, and all of them immediately converted to the enolate. The enolate looks around for a soft place to land, sees no parent, but sees an abundance of the aldehyde. It goes after the aldehyde, converts it into the species. Then the third drop hits, and so on and so on and so on. So we can effect a practical cross-aldol reaction if we add slowly the enolizable carbonyl compound to a rapidly stirred solution of the non-enolizable carbonyl compound with the base. And that is the only way to effect a practical cross-aldol reaction. Okay, so there are a couple points to make. So you remember that we said if I make this enolate, well, let's back up. If I make this aldol, I might have to heat this to 80 degrees Celsius to get this one to dehydrate into product. Okay? On the other hand, if I had this species, maybe I can do this at 60 degrees. And the reason quite simply is that the alkene unit is more stable. It's more stable, it forms faster because it's an endotherm. So any factor, any feature that stabilizes the alkene of the alpha, beta, and steroid carbonyl will facilitate its formation. Now, these R groups stabilize the dol-1 by induction, right? They're electron-releasing groups by induction, so they stabilize it because these carbons are electron poor. Well, suppose I make this compound, right? Suppose I make that compound, right? Carbonyl, OH, benzene ring. This compound will dehydrate in a flash because the product of the reaction is not only stabilized by the carbonyl, by resonance, which it is in all of these, but this benzene ring is adjacent to this one, so there'll be a significant resonance stabilization here. So in fact, the temperature at which this one is going to go is probably about minus 40 degrees Celsius. So in fact, I will not be able to isolate this compound at all at room temperature. It'll dehydrate too easily, right? And that's what we saw here. As the alkene became increasingly stable, the ease of dehydration increased. So I needed 80 degrees, then 60 degrees, another one might be 20 degrees, another one might be minus 10. This one will dehydrate so rapidly you cannot isolate it at room temperature. If I wanted to make this compound and store it, I'd have to keep it cold because this compound will dehydrate in an instant at room temperature. So I would probably have to run this reaction at minus 40 degrees to get any appreciable yield of that compound. Okay, that's point one. Point two is that aldehydes and ketones that are enolizable belong to a very wide class of compounds that have what are called active H's. And what is an active H? An active H is a hydrogen that is adjacent to an X multiple bond Y site. So that if I pull the H off as H+, the anion is resonance stabilized. So we've seen that enolates have active H's, right? It's an H that is adjacent to alpha 2 and X double bond Y. So that when the proton is pulled off, the species is resonance stabilized. Right? That is my definition of an active H. Great. What other examples then might have active H's? Well, certainly if I had an H of, say, acetonitrile, that H I would consider as being active. Because when I pull off the proton, I generate a conjugate base that is resonance stabilized. So that's an active H. What about in nitromethane? Right? What about nitromethane? Well, that's an active H. So if I pull off this proton, I generate a conjugate base that is resonance stabilized. Okay? So there are a whole series of compounds that have active H's. In other words, active H's are not the purview solely of aldehydes and ketones. Compounds with cyano, with nitro, with nitroso, with sulfonyl, any number of these compounds are going to have active H's. And although the aldol reaction itself is unique to aldehydes and ketones, there are aldol type reactions that other species with active H's can undergo. And a classic example is the following. If I take this compound is the aldehyde of furane. It's called furfural. If I treat this with nitromethane in the presence of base, what do I get? Well, if I look at this, hopefully I'll recognize that nitromethane is a compound with an active H. So I would start off by saying, what will happen, behave, is the nitromethane will be deprotonated to generate not an enolate, but an enolate type species. It actually has a name, but we're not going to get into that. There's enough vocabulary for you guys to learn. That entity can function as a nucleophile, the same way the enolates do. And aldehydes are wonderful substrates for these types of reactions. So it will attack, and I will generate this entity. N double bond O, O minus, plus, single bond, C, OH, and then the O, I'll make that species. Okay? And so I've skipped a step because I should get O minus, and then I'm going to protonate the O minus, and I'm going to get that species. But if I look at it, this species can also dehydrate, right? There's an H here. And because I have the aromatic ring adjacent to this structure, this will dehydrate in a flash. So I'm going to end up with this species, double bond, right? I'm going to make that compound. So I'll have, double, single, double, single, double, single, double. So I'll have extended conjugation, and that means that this product, which is the one I'd expect to form, will not stick. Just like the case with the benzaldehyde above, right? This compound is going to dehydrate very, very rapidly. So this is not an aldol reaction, but it's called an aldol type reaction. And in fact, when we set up the reactions of my carbonyls, you recall one of them we identified, which was way back, is we said they were Michael type reactions. And so we're going to look at those in a little bit as well. So aldol type and so on. All right, let's look at their reactions with halogens. We're looking at the reactions of enolates with halogens. So we're going to call this now, is this 4? Crikey. Is this 4? I think so. Should have looked at the bloody number when I was there. So 1, 2, 3, odd. Yeah, 4. So let's look at number 4. Get whiplash. This is the haloform reaction. If I take a carbonyl compound, let's say acetone, and I treat it with warm basic iodine, aqueous iodine, what I get as my products would be, if I used acetone, I'd get the acetate anion and CHI3. This compound is called iodoform. There, if I have CHX3, where X is chlorine, fluorine, bromine, and so on, these compounds are called haloforms. So I have fluoroform, chloroform, bromoform, iodoform. The haloforms are similar in the sense that they're all relatively polar, but none of them dissolve in water. Fluoroform, chloroform, and bromoform are all dense, colorless liquids. Iodoform, on the other hand, is a yellow solid, right? So these three are dense, colorless liquids, which are not miscible with water. Iodoform is a yellow solid, which is also not water soluble. Okay, so it precipitates out once you make it. Now, I'm going to come back to this sort of philosophical, but I'm going to point out, look here, I have 1, 2, 3 carbons, right, in my substrate, but in my product, I only have 2 carbons. The third carbon came off as iodoform. So really, this is a degradation, right, which we met in class when we looked at the Biovilliger reaction as an alternative, for example, to ozonolysis. Well, this is your third reaction that can do a degradation, although there's some more specifics with it. And you also notice that I'm going from the ketone to the acid. So I actually am oxidizing the ketone, again now, as we did by Biovilliger. But when we oxidize the ketone, we suffer degradation. We suffer breakage of the carbon-carbon bond. That's exactly what we said with the Biovilliger. With the Biovilliger reaction, if I treat this with a peracid, right, what that would make would be the corresponding ester. Right? So we're at the acid level again, but we have fractured, in both cases, the carbon-carbon bond. Now, I could eventually get the species if I treated that with H3O+, for example. I could make the carboxylic acid, right? So I could get rid of the methyl group completely. But both the Biovilliger and the haloform are similar in the sense that they will allow me to oxidize the ketone, although this is a bit more specific. But when I do the oxidation, I suffer carbon loss. I suffer breakage of the carbon-carbon bond. All right, so what's the mechanism of the haloform reaction? Well, as you might expect, in the presence of base, the carbonyl compound undergoes enolization. So we deprotonate and we generate the corresponding enolate. The enolate is generated in a matrix that contains a halogen, which, as we've seen, halogens are good electrophiles. That's why they react with bromine, with alkenes in carbon tet. So what I'll generate is the substitution product. This is a nice simple SN2, and I'll make this compound, which is the alpha halo, in this case ketone. But the alpha halo ketone is actually more acidic than the parent ketone, because I now have the advantage of induction by the halogen. Well, we're under basic conditions, and so it's not surprising then that this will get deprotonated again, somewhat more easily this time, and more completely, to give rise to the enolate, which again is stabilized by resonance and now by induction. But again, I'm generating the enolate in a medium containing the halogen, and so we're going to get attack. We're going to lose the halide ion, and we will make this species, which is the, I'll draw it this way instead. This is the alpha-alpha dihalo ketone. Right? This is my alpha-alpha. Should go this way. This is my alpha-alpha dihalo ketone. Well, again, that's even more acidic than its predecessor. In the presence of hydroxide, and these are all acid-base reactions, we can get deprotonation. I'm going to lose water. And that will generate the corresponding enolate. And you can already tell where the story is going. The enolate is generated in a medium that contains the halogen. It's assuming we have excess halide, right? And that's going to give rise to the alpha-alpha-alpha tri-halo species. Alpha-alpha-alpha tri-halo ketone. But something interesting was happening as we were sequentially replacing the H's on the alpha carbon by halogens. One thing was we were removing the H's. But also, every time we put an H on, every time we put a halogen on, we started bleeding electrons from the carbonyl. Right? So one H, by induction, would bleed electrons from the carbonyl. That would activate the carbonyl. Two H's would bleed more, activated more. Three halogens would bleed even more, so the carbonyl carbon now is very active. And in the presence of more hydroxide, the carbonyl becomes a target. So I attack the carbonyl carbon, and that generates O minus OH CX3. Then the O minus comes back, kicks out the CX3 minus. So I'm going to kick out CX3 minus, and I'm going to make C double bond O OH. So I've made a carboxylic acid. But this is an anion. This is a carbanion. Carbanions are strong bases. They will pull off the proton, and I will generate as my product the carboxylate anion plus CHI3. The CHI3 is insoluble, so it precipitates out as a yellow solid. The anion remains in solution in water, and I don't see it. But what I've done is I've degraded a 3-carbon compound to a 2-carbon compound. There are 2 points to be made. Point 1. This reaction should be illegal because I'm going from O minus, right, a relatively strong base, to C minus, which should be a stronger base than O minus. And so this should have broken the acid-base rule. But in reality, it's not that bad because the C is bound to 3 halogens. Right? The C is bound to 3 halogens, which are going to stabilize it significantly. So this is not as unstable as it seems. It's still slightly stronger than the O minus, which is why the reaction is slightly heated. Because if you look, 1 particle generates 2. So there's a 50% increase in the energy carriers. Right? We're going to go back to our delta G issue. Delta G is equal to delta H minus T delta S. And in this reaction, we are going from a weaker base to a stronger base. So the delta H here is actually positive. But it's not very positive. I do have a large positive delta S because I'm going from 1 particle to 2. There's a 50% increase in my energy carriers. And then I'm going to help it out by warming it, right? Because we use warm basic iodine. So the combination of the heat and the inherent positive delta S on the reaction makes this term bigger than that term. And overall, I get a negative delta G, so the reaction is spontaneous. All right. The other point to note is that if you look at the mechanism, it's only when the carbon has 3 halogens on it that the hydroxide can attack. In other words, For the reaction to go, I will need to have a CH3 group on my carbonyl. I must have a methyl carbonyl for the reaction to go. So the haloform reaction then will only go with certain substructures. In other words, I will need to have a methyl carbonyl. In other words, a CH3 next to C double bond O, because only, and of course, this compound has to be an aldehyde or a ketone. It couldn't be an acid or an acid halide, right? It has to be an aldehyde or a ketone. The compound has to be a methyl carbonyl, so I have the three H's that can be replaced by halogens, right? Or something oxidizable to a methyl carbonyl. And that would have to be a methyl carbinol with this particular substructure, right? A methyl carbinol. A carbinol. But I must have an H on this position, otherwise it's not oxidizable. And the reason methyl carbinols work is that iodine is an oxidant. So the iodine will oxidize the methyl carbinol into the methyl carbonyl. It's the methyl carbonyl that actually undergoes the reaction. Right? That will give you CX3. Right? That will give you CX3, C double bond O. Right? And then when my OH minus attacks, this will cleave. I'll make my my species, let's say O minus OH, CX3, and whatever was here, this comes back, kicks that out, and I make my carboxylic acid, my CX3 minus, which pulls off the proton and gives me my haloform and my carboxylate. Okay, so the iodoform reaction or the haloform reaction is unique to compounds having one of two substructures, methyl carbinols or methyl carbonyls. So let's see which of the following compounds would give me a positive haloform reaction. So tell me which of these compounds, if any, will give me a positive haloform reaction. Okay, so again, we need one of two substructures, methyl carbinol or methyl carbonyl. I might as well do another one. Let's do this one. Okay, which of these compounds will give a positive haloform reaction? In other words, when I warm it with basic iodine, I will see a yellow precipitate. Okay, this is out. That's a carboxylic acid. The reaction is unique to compounds at the aldehyde level, at least as the active agent. So that's out. What about ethanol? Well, ethanol has a CH3. Ethanol has a CH3, CHOH. So ethanol is this compound. So it clearly has the correct substructure. So ethanol will give the reaction. What about methanol? Well, methanol is CH3OH. That doesn't have the substructure. So methanol does not give me a positive haloform reaction. What about this ketone, the one we made earlier? Well, it's certainly got a carbonyl, and it certainly has methyl groups on it, right? But look what the methyl groups are. They are CH3C with no H's, then another C and a carbonyl. So that's not going to work, right? Because the CH3 has to be adjacent to the carbonyl. Even if I had its isomer, this compound, right, that won't work. It's got CH3C, then the carbonyl. So neither one of these will give a positive haloform reaction. What about this one? CH3 C double bond H. CH3 C double bond H is allowed? Yes. This one, CH3 C double bond something at the aldehyde level? Absolutely. This one, well, it's not even a CH3 in this mixture, so that's out. But of course, if I had acetophenone, right? This is CH3 C double bond O, right? And the alkyl group, that would work. So this won't. What about this one? CH3 C H OH and then something. Absolutely. This one, CH3C, no H's. So we are out. So I can tell which compounds can give a positive haloform reaction. Now, what is the value of the haloform reaction? So the value of the haloform reaction is twofold. One, it's qualitative. In other words, it allows us to identify the presence of certain substructures in my compound. If I know my compound is an aldehyde or a ketone, which I might know because I get a positive 2,4-DNP test, right? So I get a yellow to red precipitate when treated with 2,4-DNP. What I would do is I could treat that compound with warm basic iodine. And if I see a yellow precipitate, then my compound is going to have that substructure. Now, alcohols could give the reaction as well, but they would have this substructure. So compounds giving a positive haloform test would have to have one of these two substructures. So that's a lot that I know right there. The other value of the haloform reaction is synthetic. Because what it does is it allows me to convert methyl carbonyls and methyl carbenols, right? It allows me to degrade them specifically at the methyl group. So if I use warm basic iodine, what I would get would be the carboxylate and CHI3. I'm not so concerned with this, I'm concerned with that. So this allows me specifically to excise the methyl group. See, when we do biovinegar or when we do ozonolysis, we can chop off 1, 2, 3, 20 carbons. Doesn't matter, right? So if I have this alkene and I make a double bond here, I can chop off a bunch of carbons. If I have this ketone, and I have a carbonyl here, and I do biovinegar, right? Let's see. And I do biovinegar, I'm going to end up with this compound. And when I hydrolyze, then the whole cyclohexyl group comes off. So the reaction is, for biovinegar and ozonolysis, I can lose 1, 2, 3, or any number of carbons depending upon the structure of the molecule. But the haloform reaction is much more specific. It will specifically take off a single methyl group. So I can use it from a synthetic perspective. This is a degradation, but I'm only getting rid of a single carbon, right? So if you're given a question where you're doing a degradation, the question you're going to have to ask yourself is, well, how many carbons am I losing? And if I'm only losing one, I might be thinking of the haloform reaction. If I'm losing more than one, well, it's not haloform. It could either be the biovinegar or the ozonolysis. In the same way, if I'm bringing on one carbon, I'm thinking maybe cyanide, right? I'm not going to be thinking, of some other species which has multiple carbons. Okay, so we will call this quits, and we will pick up from here next day. All right.